Welcome to this May webinar in the ASCCT and European Society for Toxicology in Vitro webinar series. I'm Christy Sullivan. I'm the secretary of the American Society for Cellular and Computational Toxicology. I want to encourage everyone to visit our websites to learn more about our organizations and consider becoming a member to support programs like this webinar series. You can also join our mailing list for job and event announcements relevant to the in vitro and in silico toxicology community. The webinar is recorded, and the recording will be posted on the ASCCT website a few days from now. In the webinar platform, you can ask questions of the presenter using the Q&A feature at the toolbar at the bottom of your screen. We'll have a Q&A period after each presentation is finished. So please add your questions at any time, and the other participants can also vote up your questions if they want to hear the answer to them as well. We have enabled closed captions, and you can turn them on or off in the toolbar as well. And I hope you'll say hello in the chat and let us know where you're joining from. I just have a couple of brief introductory slides, which I'll go through now. The first is that the ASCCT is having its 15th annual meeting. I can hardly believe that this is where we are already. So we will have this meeting in late October. You can see the main meeting will be October 27th through the 29th. We will also have an ancillary meeting on October 26th, the day before, with the Society for Adverse Outcome Pathways, which is part of the ASCCT and an organization that's interested in advancing adverse outcome pathways for regulatory toxicology. Everything will happen at the Durham Convention Center in Durham, North Carolina. And we are open right now for session and continuing education proposals. That should not say May 1st, that should say May 26th is the deadline. So you still have a little bit of time to get those proposals in. And then if you want to submit an abstract for a regular submission, that deadline is July 10th, as well as the travel award deadline. So we give away travel awards for people to attend the meeting. We also give awards during the meeting. For some of them are for anybody, but some of them are also targeted at students and early career scientists. So really encourage you to join the meeting and encourage your students and trainees to join as well. You can take a look at our website to see an entire list of upcoming events. These are both ASCCT events, and also some of our partners have webinars as well. The next ASCCT-ESTIV webinar is going to be focused on global medical device updates from Dr. Kelly Coleman and Lindsay Borton. That is going to be the last week of June. We're just kind of finalizing the date now, so you'll be able to register very soon, but stay tuned for that. And then I will now go ahead and introduce our current speakers for today. Both of these presenters, have won awards at our most recent ASCCT meeting, the 14th annual meeting last October. So congratulations to both of you for that. The first speaker is going to be Shaun McCullough. Dr. McCullough is a senior principal respiratory scientist at RTI International, where he leads the predictive toxicology and exploratory biology group and the in vitro respiratory modeling and toxicity testing laboratory. Dr. McCullough works closely with stakeholders on efforts to develop and deploy organotypic models of the respiratory tract in research and testing, build confidence in the use of in vitro systems and assays for inhaled chemical hazard identification, characterize inter-individual variability in vitro models, and establish cross-sector harmonization of in vitro assays for inhalation toxicology to support regulatory acceptance. In recent years, Dr. McCullough's research has led to the development of two novel multicellular in vitro respiratory tract models, and he has served as a subject matter expert for the review and development of guidance related to the use of in vitro models and data for a diverse range of federal and international organizations. Our second presenter is Dr. Sezin Aydin. She is a research associate at the University of Pennsylvania and a translational bioengineer focused on developing um, human relevant microphysiological systems for mechanistic toxicology. Her current research focuses on organ on a chip and vascularized tissue models that recapitulate human barrier function and tissue microenvironments to investigate injury mechanisms and identify predictive biomarkers. She has led interdisciplinary government and foundation funded projects spanning inhalation toxicology, oral and mucosal exposure, and neurovascular biology with the goal of advancing more predictive human relevant approaches while reducing reliance on animal models. So, welcome to you both, and now I'm going to turn the floor over to Dr. McCullough.
All right. Can you see my slides and hear me?
Yep, everything looks
All
good.
right, great. Well, first of all, thanks for the invitation to talk. I'm very pleased and honored to be able to present the work that my team did on this project, where we were focusing on evaluating the health effects of HFPO across three regions of the respiratory tract. So, in brief, inhalation exposures are a ubiquitous part of our daily life, and these come from a range of sources, including environmental pollutants, industrial and occupational exposures, personal care, and commercial products. And importantly, the actual exposure within the respiratory tract to these different exposures differs, and the effects differ based on the region of the respiratory tract. And one of the big challenges with the traditional approach to evaluating potential hazards here is that animal models aren't really a great representation of the human biology here and human outcomes. And some just brief examples. So rodents are obligate nose breathers. Humans are not. We're oral nasal augmenters. There's a difference in respiratory tract architecture. And then they're not very great for evaluating mechanistic data or generating mechanistic data for evaluations and understanding the individual components of an adverse outcome pathway. And so, as a really quick overview, a number of years ago, and it's hard to believe almost 10 years ago, there was a very kind of pioneering case study that the EPA ran through OPP, or the Office of Pesticide Programs, using chlorothalonil as case study to use in vitro models to inform the risk assessment for chlorothalonil's re-registration. And at the time, this was a very big step, and it's a good foundation for moving forward. And they used an epithelial only model. I'll explain that a little bit more in a second. They focused on the nasal region due to the evaluation of the material exposures. They focused on cytotoxicity and epithelial barrier integrity as endpoints. They conducted a single 24-hour exposure. The test article was delivered by something called liquid application dosing. In this case, chlorothalonil is a pesticide that's applied in an aqueous solvent, so the exposure occurs by respiratory droplets, or excuse me, by droplets into the respiratory tract. And actually, a big step ahead of their time was that they used 5 donors. However, in the analysis of the data, they didn't consider inter-individual variability because people weren't really thinking about that back then. And so time goes on. All right, like I said, it's hard to believe it's almost 10 years after the fact from that. And so now thinking about how do we use the current state of the science to increase the evaluation, or the relevance and accuracy of the evaluation of these exposures with in vitro systems. We move into now what we'll be talking about today, which is the study that addressed the first requirement for an in vitro respiratory study set forth in a Toxic Substances Control Act, or TSCA test order. And so our approach to this, we tried to update the state of the science in our approach based on recent observations and publications. And so we used donor-matched ALI, or air-liquid interface differentiated co-culture models. We used a much more in-depth battery of in vivo relevant in vitro endpoints, and I'll cover most of those in the talk today. We included single and repeated exposures, which was a requirement of the test order. And we conducted the exposures under ALI conditions, which is more relevant to the respiratory tract. It was sort of required in this case because HFPO, the test article here, is exposures occur by gas. So not really a good way to put it in a liquid. And then we leveraged models across 3 different regions of the respiratory tract, which I'll go over in a second. And then we also used 5 donors, and we did the analysis to incorporate consideration of inter-individual variability. And while 5 donors is not in itself representative of the human population, it does give us insight into how some donors may be more responsive than others. So our first step is improving the biological complexity of an in vitro system. So this is a representation. So there's a tissue section on the left here. Oop, it's going ahead of me. That's showing the respiratory epithelium. You have ciliated cells and goblet cells. Goblet cells secrete mucus. Then the ciliated cells brush the mucus and whatever it traps up the mucociliary escalator, which is one of my favorite words. And you either cough it out or you swallow it. And then this architecture also has basal epithelial cells, which are sort of at the base of the epithelium and serve as the kind of progenitor cell that can facilitate repopulation. And this is an illustration of what that looks like here. Make it a pointer. This is what that looks like as an illustration in a cell culture insert. So we got a porous membrane here with the epithelial cells here, and then they secrete a thin layer of mucus, and there's some periciliary liquid under here. And this is what it looks like if you do histological evaluation with hematoxylin and eosin staining. So this is general architecture. And this looks very much like what it looks like in vivo. And so now if we kind of zoom out a little bit and look at what the rest of the tissue looks like, all these light pink cells here are stromal fibroblasts. There's a basement membrane under here, and there are a bunch of other accessory cell types. We focused on what is most practically deployable here, which is just integrating the fibroblasts to go to a donor-matched co-culture. And this is what that staining looks like, and this is an image that was provided by Epithelix of the airway epithelium. And then this clear thing here is the membrane, and then we get the fibroblasts underneath. And so this is more representative of the architecture in vivo. And one of the reasons that we thought it was so important to include those fibroblasts in there is that epithelial cells play a big role in the respiratory tract biology and its role as a barrier to inhaled insults. But fibroblasts also play a critical role there in structure and function. Basically, fibroblasts have a terrible publicist, and people don't think about them nearly enough across tissues in general. But we've done some studies over the years where we have integrated some of these stromal cells, and we see that fibroblasts are both targets and mediators of exposure effects. And just as a quick example of that, here ours is a principal component analysis plot of some RNA sequencing data from a study where we looked at the dose response of epithelial fibroblast co-culture to a gas called acrolein. And basically, here are all the epithelial cells, and here are all the fibroblasts. And I think this is a very good way to capture the difference between these cells and the way that they respond to insult. And so here are the actual models that we used. So this is the Epithelix mucellare HF. We use this platform for both nasal and bronchial tissues. And we've got nasal here on the left, bronchial on the right. Overall, the architecture is going to look very similar here. And the top here is hematoxylin eosin, or H&E, which just shows us general architecture. And then this is Alcyon blue PAS, which is going to stain mucins. And so it's showing us these darker stained cells here. These are mucin granules in goblet cells. So this gives us a good idea of the goblet cell density. For the alveolar region of the respiratory tract, we use the MatTek epialveolar model, which is actually a tetraculture where we have donor-matched alveolar epithelial cells and interstitial fibroblasts. You have primary human lung microvascular endothelial cells on the bottom of the membrane, mimicking the blood vessels that surround the alveolar space. And then they also include a THP1 cell-derived macrophage-like cell to mimic alveolar macrophages. And then here's the histology there. This is not a mucus-secreting culture, so there's no mucin staining here. And so when we want to think about the variability in a human population, this also is another big limitation of animal models, where animal models are intentionally inbred. And so as you can kind of see here, you breed and breed and breed, and these are supposed to be sort of genetically homogeneous. When we use cell lines for things, yes, you have a human-derived material. However, in addition to these cells are typically transformed or derived from a tumor and have some genetic abnormalities, and they can drift over time. All that aside, they're theoretically isogenic, and so they should have the same genetic makeup from passage to passage to passage. So again, not a really good way to look at variability. And so when we have primary cells, we can isolate cells from individual donors and generate cultures out of those. And in this case, again, we're using donor-matched co-cultures, so the epithelial cells and fibroblasts are from the same donor. And why does that matter? We've shown in previous work that the range of outcomes can vary considerably with donor. This is just cytotoxicity, and you have a range effectively from minimal cytotoxicity to completely dead. This is variability and barrier integrity. Everybody tends to go in the same direction, but what you can see here is there's a lot of range in both starting point and kind of the way they get there. And then if we look at another common endpoint for respiratory toxicology, secreted IL-8. So IL-8 is interleukin 8. It's a sentinel cytokine for the pro-inflammatory response and promoting neutrophil infiltration. Everybody is, again, kind of going in the same direction, but there's a lot of range in outcomes. And the reason I put these data up there is just to think about when we consider the way that that studies are typically done, especially in the published literature. You typically see one, two, maybe three donors if you have primary cells. And so if you use a small number of donors, you're kind of rolling the dice as to which one of these individuals you get or a group of them. And you can easily see how either you can overpredict, underpredict, or just get a range that would give you a non-statistically significant result that would draw scrutiny from your reviewers as to whether it's valid. So for our HFPO exposures, we had acute and repeated exposures. So the acute exposures, these are both 4 hour per day exposures. Acute exposures, we looked at tier 4 hours post and 24 hours post. And then we also looked at cytotoxicity, MUC5AC, which is a commonly evaluated mucin, part of mucus. And then we also looked at soluble mediators, interleukin 8, IL-6, and vascular endothelial growth factor as an indicator of potential remodeling. And we did this across all three regions. In the nasal and bronchial, we did TNF alpha. And then in the alveolar model, we did GM-CSF, IL-25, and TGF beta as well. When we translated to the repeated exposures, we only use the nasal and bronchial models for these same endpoints with the addition of histology, where we looked at general architecture, goblet cell density, and we did immunostaining for FOXJ1, which is a transcription factor that will localize in the nucleus in ciliated cells, and similarly P63, which is also going to localize the nucleus of basal cells, so it facilitates counting. And overall, this is our acute study design. I won't belabor this for time, but we've got, again, 4 hour exposures under ALI. We use a range of concentrations of HFPO from 100 to 2500 ppm. These concentrations were selected based on the existing in vivo data from the test order docket. And prior to conducting HFPO exposures, we did a decent amount of characterization of both flow rate, CO2 concentration, ensuring humidity to see, basically make sure that under these conditions, are we going to cause an effect on the cultures and have kind of a two-hit outcome. And so we settled on a flow rate that did not demonstrate cytotoxicity and a CO2 concentration that did the best job at maintaining a target medium pH. Just really quick note here, this kind of step is really important, as we didn't realize it going into this, but it was apparent very quickly that the ALI maintenance medium provided by Epithelics and that provided by MatTek behave very differently in ambient and CO2 supplemented environments. So we ended up having to use different CO2 concentrations for the different models because they use the different media. So it's, I'll put a plug in here for characterizing your test system before you use it. And we did use CO2 for pH buffering in these bicarbonate medium because using HEPs, there are papers that go back to the late 80s showing that HEPs, which is a non-CO2 dependent buffer, will actually, in the presence of light, cause reactive oxygen species generation and potentially impact cytotoxicity. So we wanted to avoid that. So really quick, in our acute exposures, we saw a very mild, so yes, we've got a bunch of asterisks here, a lot of statistical significance. That's great. But these are very small. Note the y-axis here. These are small changes. And I was very surprised. We ran these analyses several times, given that we were seeing a very significant effect at a very small effect size. But these hold, and this is especially interesting for us seeing this across 5 donors. Part of this is, this is clearly a consistent effect. But this is also, we were very particular about the timeline on these. So the time points here are plus or minus single digit minutes instead of plus or minus an hour, which is not atypical. Similarly, we saw a very mild cytotoxicity in the bronchial cultures, and the way that I'm presenting these data, so the top graphs with bars are the mean and standard deviation of the group, and then the trace lines here are the individual donors. So this would be mean and standard error for error bars, and a lot of these are pretty tight. In the alveolar model, so this was only available, so epialveolar prior to the study was only available commercially from one donor. So part of the study was sponsoring their production of a second donor just so we could see some level of variability. So we've got the standard STD and then the alternate ALT donors here. And so there is a lot of variability, but we don't really see a lot of cytotoxicity in these exposures. We did see, and so for time, I'm not going through all the individual cytokines that we looked at. The take home here is there's a lot of variability in the response overall. HFPO exposures, even through 2500 ppm, did not have a lot of effect on cytokine induction in these other cytokines, with exception of a few donors, which were relatively strong responders. And in some cases, the effects were non-monotonic. So for sake of time, I'm going to focus on the alveolar outcomes because they also fit very nicely with the known in vivo data. So we saw, and there's a little bit of backstory on these 100 and 400, so you can disregard these in terms of what we would consider a biologically meaningful effect and focus on these higher concentration outcomes. And so we see an uptick of IL-6 and of VEGF alpha in the medium of these alveolar cultures. And these heat maps are just showing the level of significance at the group level and the individual donor level across the concentrations. And so what does that really mean? When we look at the outcomes across the models, nasal and bronchial models, very mild toxicity. And then we really have non-monotonic effects. We didn't really see much on TEER or MUC5AC. And so this actually aligns very well with the extant in vivo data where there weren't really a lot of HFPO specific effects on the nasal and bronchial regions, apart from a little bit of nasal discharge at high levels in in rats that was associated with concentrations that cause death by pulmonary edema. And so in the alveolar model, to get to pulmonary edema, we did see increased VEGF alpha, and VEGF alpha is very strongly linked to or as a driver of pulmonary edema. So if you overexpress it in animal models, you get pulmonary edema. If you block it during injury, you can prevent the induction of pulmonary edema. So there's a lot of strong evidence there linking VEGF alpha to pulmonary edema. We did see increased IL-6 secretion. This is not necessarily linked to pulmonary edema, but it does show that you're having some insult that would maybe induce some inflammatory infiltration into alveolar space, and no cytotoxicity or barrier integrity changes. So ultimately what we're seeing is that in the alveolar model, these exposures are causing an event that is in the adverse outcome pathway for pulmonary edema. So then we move to the repeated exposure arm, and we use the data from the acute nasal and bronchial cytotoxicity to identify, initially it was a low-EC and a no-EC, but those concentrations were pretty close to each other. And so in consultation with EPA, we separated and we dropped the lower concentration down a little bit to at least give ourselves a twofold range of concentrations. And so in this case, we're doing 14 consecutive daily exposures at 4 hours per day to these two HFPO concentrations, along with matched clean air or vehicle and incubator controls. And this is a key component that's often lacking from these studies, is the inclusion of these matched incubator controls, which are effectively a sham control if you think of it in an in vivo context. And what this does, especially as we learn more about these in vitro systems, it allows us to record whether the repeated clean air exposures themselves have an effect on the test system. We didn't use that as a modifier in the interpretation of these data, but we do report it just because it's important to pay attention to these things and build an understanding for what this may mean. And then I already went over our endpoints here. And just to be clear, these are 14 consecutive daily exposures, so no breaks for the weekend. So what we saw here, I didn't show the graphs, but we did not see cytotoxicity at either of these concentrations, even though we do see cytotoxicity at 1770 ppm in the acute exposures. So that either shows that the cultures are adapting, or for whatever reason, there's not cytotoxicity after the 14th exposure. We did see an increase in epithelial barrier integrity as measured by TEER or trans epithelial electrical resistance in both the nasal and the bronchial cultures. And how we interpret this is that's probably suggestive of remodeling. And luckily for us, we were planning to look at remodeling anyway. And so then, in addition to looking at H&E sections, which showed some basic vacuole formation, but not a lot of overt pathology in these outcomes, and I've spared the data for sake of time. We did see with immunostaining, or excuse me, with Alcium Blue PAS, we counted basically goblet cells per linear field and adjusted that for the length of the linear field. But overall, we saw a decrease in nasal goblet cell density. That's pretty substantial here at about 50% loss. And this is tracing down by donor. And then these are the Alcium or representative Alcium Blue PAS images from Clean Air Control 880 and 1770 ppm. Then we tracked the ciliated and basal cell densities by immunostaining with FOXJ1 and P63, as I mentioned earlier. This is just a representative image showing you what this immunostaining looks like. And then we had a very arduous work by some of our technical team to manually count these. It took quite a while, so thanks to them for doing that. And that allowed us to look at the relative density of these per total number of cells as determined by DAPI positive cell nuclei. And so in the bronchial model, ciliated cell density goes up. It's not changed in the nasal model. And then in the nasal model, basal cell density changes at 880, but not 1770 ppm. So whether this is a sort of real effect or just normal variability is open for interpretation. It's one of the challenges with the 5 donors. It gives us more than 1 or 2, but it's not necessarily a full population. And another quick note on that is one of the things that is kind of yet to be established in the field is how do we develop a reliable sample size estimate for these kind of studies? So food for thought moving forward. And then as a quick summary, in the nasal epithelium, so repeated HFPO exposures give you an increase in epithelial barrier integrity or resistance and a decrease in goblet cell density. Interestingly, this did not translate into a change in the secretion of MUC5AC. And then in the bronchial epithelium, these exposures increased tear and ciliated cell density. So overall summary here, acute exposures have very minor effects in the nasal and bronchial regions, and this aligned with the lack of nasal or bronchial HFPO-specific toxicity in vivo. In the alveolar region, we did see HFPO-induced VEGF alpha, VEGF-A secretion, which is early in the adverse outcome pathway for pulmonary edema, which aligns very well with the pulmonary edema observed in multiple in vivo studies. And then repeated exposures. Again, no evident nasal bronchial toxicity. And one thing that we couldn't evaluate alignment with existing in vivo data is the remodeling, because the in vivo data did not go into that level of detail in terms of specific levels of epithelial remodeling. So if we have any questions, I'd also like to acknowledge my team. So this is my overall predictive tox team. Aaron Huber was our lead biologist here and really, did the really brute work to get this done and really run these on a very tight clock, which was, I think, very pivotal to getting the reliability of the outcomes here. And then we had a bunch of other contributors, especially Ryan and Clint, who built our very complicated exposure system on here and did all the maintenance for us. This study was sponsored by the American Chemistry Council's HFPO Test Order Consortium in response to the TSCA test order for HFPO issued by EPA under TSCA. And that's it for me.
Thanks very much, Shaun. We have a number of questions, so I'll get right to them. The first one, is there a specific reason that you chose epialveolar instead of the Epithelix alveolar air model?
Yes, a very simple one. Epithelix did not sell it commercially. Like they wouldn't ship it to you. They use it
Yeah.
in-house at this time, but it was
Okay.
not available for purchase into the lab. There's also important note there. The two models differ. The Epithelix model is alveolar epithelial cells with microvascular endothelial cells, and then the epialveolar model has the 4 cell types. And so there's a biological difference, but also there was a logistical difference there as well.
Okay, thanks. What are the ratios of fibroblasts to epithelial cells in the different models, and how do they reflect the ratios in vivo?
I don't know the specific ratio in the in vitro model, but what I can tell you is that in the in vivo comparison, there are many fewer fibroblasts in the in vitro system compared, like if you just look at the depth of the stroma under the epithelial layer in vivo, there's a lot
Mhm.
of mass there, and so it's not really feasible to capture that with an in vitro system. Uh, at the moment. That's something that if somebody wants to, we think about this a lot and sort of how can we overcome that limitation. So if somebody has an idea, I'd love to see it, or if they want to collaborate on developing that. As Christy highlighted in the beginning, we've developed a couple of models, but we've always separated the fibroblasts into the well because it gives us a lot more sample to work with when we're looking at things like sequencing or protein. You just don't get a lot of fibroblasts. The surface area of the well is pretty small, and fibroblasts don't have a lot of a sample material in them. So anyway, I would love to have that as an option moving forward.
Okay. And just to clarify, when we're talking about in vivo, are we talking about humans or rats,
Hu
or they're both
Human.
the
My
same?
my
Yeah.
my comparison is to human.
Okay. Me too, but I just was making sure. Okay. What is the rationale behind using different panels of cytokines between the nasal, bronchial, and alveolar models?
So the nasal bronchial panels were the same, just to clarify that. And then the alveolar model, EPA dictated the use of GM-CSF, IL-25, and TGF beta. The TGF beta to look for remodeling, and then IL-25 and GM-CSF to look at immune cell recruitment and activation, secondary to potential immune related outcomes of exposure.
Okay. Um, I'm not sure if you know, but what is your safe exposure for humans to HFPO?
In terms of in the laboratory conducting these exposures or in the occupational
I'm
setting.
well, this is what the question says, but I'm kind of
Uh,
wondering if they're saying based on your in vitro data.
so based on the in vitro data, that was not part of the scope of this
Okay.
project. This EPA was very direct in just wanting the effects outcome
Yeah.
data, not the sort of integrated analysis of what does this mean and back calculating into real world exposures. But it does highlight one of the important considerations when interpreting in vitro data in the respiratory tract and elsewhere is it can be perilous to assume a direct comparison between sort of the nominal or target concentrations of the test article in an experimental system, and that the mass transfer of that in the case of a gas is going to be equivalent to the mass transfer in a human or an animal model. And that's one thing that would have been it would have been great for EPA to have required that because it would answer a really fundamental question about how do we extrapolate from some of these in vitro models to in vivo outcomes at the human or rodent level.
Yeah, I mean, I know, chlorothalonil did a lot of work around that, but I would say sort of the external to internal exposure for inhalation is a big area for
Well,
study and modeling, right?
yeah, and with one of the benefits that chlorothalonil had that we didn't is they focused on the dosimetry based on particle expo like the particle size and aerosol exposure, which is 1,000% easier to do. Like it's a lot easier to model particle deposition than it is to model gas mass transfer. Without so you can do the aerosol or particulate dosimetry with some pretty readily available tools such as MPPD or CFD modeling, um, looking at uh, mass transfer from a gas requires actually measuring the mass transfer into the system. It's just basically a lot more complicated because it's less well defined. That's not the right way to say it. Let me just leave it at it's more challenging than particles for time.
Thank you. We have several questions. I'm going to ask you one more quick question and then we're going to let you maybe answer them while Sezin is presenting. But this one I thought people would want to hear. So regarding the exposure condition, since HFPO is a gas, did you take special precautions when exposing the model? For example, were culture plates enclosed in a Tidlar bag during exposure?
So yes, and yes to the first, no to the second. So we use the CellTox in vitro exposure systems by MedTech Biolab. And so those are sealed systems, and then we ran the outflow into basically up through our fume hood exhaust, which is handled. Say we had EHS was all over this, as you can probably imagine. There's no official PEL on HFPO, but we basically treated it at zero point 0.1 ppm. Exposure at any time was considered hazardous. So we were very cautious to make sure that we were shunting everything out of the exposure system into the exhaust gas flow, where it gets significantly diluted before flowing out of the building. And we also were doing it prior to exposures when we set this system up. Most of the tubing is stainless steel that then we pressure tested and routinely rechecked to make sure that we didn't have any leaks, and actually even came up with, since just as in an abundance of caution, and this is just me geeking out a little bit because I think it's cool to think about this stuff. It also helps keep my team safe, where we had an electronically controlled solenoid valve immediately downstream of the regulator that was then on hooked up to the emergency power, where even if there was a power failure, if emergency power failed, then gas stopped, kind of thing. So it's sort of even to try to anticipate any personnel exposures that could cause hazard to the team. We're trying to anticipate that to even in a system that is sealed and pressure tested. You never know. You don't want to find out the hard way. So we were very conscious of what that exposure could be, and also that also allows, in addition to keeping the people safe, it allows us to be much more confident that what we're sending into the exposure system is actually in the exposure system for the exposures.
Right. Two important considerations there. All right. Well, thank you very much, Shaun.